just write it like this. We must add one space direction and one time direction. So if we have a for the Euclidean case, we'd have a SOD, then we'll add one space direction and one time direction. So the conformal group in the Euclidean dimensions is SOD plus 1, 1. Okay? And for a d-dimensional Minkowski space with conformal symmetry, the group of the algebra would be would have d minus 1, 1. So we add one time and one spatial dimension, and we end up with SOD2. Okay? And the way to see this,
these are the groups that are actually isomorphic to this one.
it turns out to be this group.
Yes, those groups are just like they have the same dimension.
Yeah, these would
These
be
are
all
the-
the possibilities.
Like the gases that have the same dimensions, and these are the groups that are actually
They actually have
isomorphic.
yeah, sorry, I should
Okay.
have.
No, just
Sure. This is the answer. Okay. This is the answer to that question. Okay? And the way to see this is to construct we introduce these capital indexes A, B, etc. They will run. Okay, let me just see how we organize them here. Okay, they run between say, what is this? Mu and then d plus 1 and d plus 2. Okay, so this mu is encoding all the indices we have in our physical space. Okay, be it Euclidean or Minkowski space. And then we just add two more indexes, okay? D plus 1 and D plus 2 at the end of the list. Okay? Then we define this, sorry about this. Define the generator, this generator. Right, just a bit below. The matrix. Here, the columns, the lines, will be this first line will be mu. Okay, this is schematic, okay? Mu, this will be d plus 1, this will be d plus 2. And for the columns, right here we have mu, d plus 1, d plus 2, okay? And then we'll just allocate all these generators inside the matrix. Okay? And if you do this like this, okay, so let me just call it nu instead of you put n nu here, the rotation generator. Then here you put mi. You have to check this if you want, but mi is. I might have put a minus sign in the wrong place somewhere here. It also depends if you're on Minkowski or Euclidean space for starters. Put everything positive here. This you can just check in any of those references I gave you in the first lecture. Okay? And here would just be, this would be an antisymmetric matrix, so here would be minus this guy. This one will be minus this guy. So if it's an symmetric matrix, here in the diagonal must be 0, here must be 0, and here we put minus d, and here we put d. Okay? Just construct this generator, and then you could just, let me see if I get this right this time. From this we can just compute NAB, MCD, and you find that it is eta BC and AD plus eta AD and BC minus eta BD and AC minus eta AC and BD. Okay, this time I got it right. Okay, this is with say this eta, this metric in this D plus 2 dimensional space is either 1, 1, blah 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 blah, 1, 1 minus 1. Okay, this would be up to here would be our original space, so this would be for Euclidean. Okay, or if we start from a Minkowski space, this would be minus 1, right? The time dimension of the physical Minkowski space. 1, 1, 1, 1, d times. And 1 minus 1, the second time dimension. Let's have for Minkowski. This is repeated d times. Okay, for both. Okay, so you see that this is just like the commutative for rotations in d plus 2 dimensional space. Okay, so this is the way to see this. That we must, this construction, or we could try other constructions, right, to scramble this thing here and try to close a similar algebra by putting more time dimensions here, more space dimensions, and so on. But you will see that this only works for this case. If you start from Euclidean space, then you must add one space and one time dimension. If you start from, you must always add one space and one time dimension. So you start from Euclidean, you have this group. You start from Minkowski space, you have this group. Okay, that's the only way, as far as I know, for this to work out. Okay, this is the way to see it. Any questions? I mean, the same for the similar reason, do not need those things that to get the conformal algebra on doing this. Okay. Just it'll be a loss of time. But is the concept clear? Okay. This is the idea. Okay. It is important to know that it is this way. And if you want to read about it, you can probably just take any group theory book or representation theory book. Or if you want to go to the base of this, the paper is, I believe, I haven't read it, but as far as I know, it's the first time it was discussed in the physical literature. It is at Dirac. I guess it was 36. It is wave equations. In conformal space. Okay. And let me also remark one last thing here is that these groups, say, let's take Minkowski for definiteness. The conformal group on d-dimensional Minkowski space is SOD2. This coincides with the isometry group of anti-de Sitter space in d plus 1 dimensions. Okay, so the conformal group on d-dimensional Minkowski space is the same as the isometry group of d plus 1 dimensional anti-de Sitter space. So this is the first clue for the ADS-FT corresponds the groups match. Okay, just a remark. This is the first clue to the ADS-FT corresponds. And any question about this? Because we're about to move to the next topic, that is the light conformalism. We'll pick up from here, so it'll be kind of continuous transition. No questions? So, how much? So we won't be getting any correlation functions today. I guess we can call this 3. This has many names. It has light conformalism, could be null conformalism, or it could be embedding formalism. All of these 3 by exchanging formalism with method. Whatever. It has many names, but any of those do. So I just call it light conformalism because I guess it's the most transparent one. And this is an idea that is again originally due to Derek in that paper. That's what he actually did on that paper. He just said, okay, conformal symmetry. Let me just remind you that the conformal transformations, they act non-linearly in the physical space. We have a d-dimensional space, so in d-dimensions, the conformal group acts non-linearly, it acts quadratically. So it's a bit different from what we use with rotation and translations or any other linear groups. Okay, groups that act linearly. But we just discussed here, this is the last remark, and that's the reason why I put it as the last remark, is the d-dimensional conformal group is it can be understood as rotations in a d plus 2 dimensional space with one spatial and one time direction added to it. Okay. So, and we know that rotations act linearly, and we're much more used to it. So the idea, Derek in that paper in 36 is to look at the d plus 2 dimensional space. Say, to understand slash implement if you want. So d-dimensional conformal symmetry. Okay, or maybe another way to put it is just to look at d plus 2 dimensional space, d plus 2 fictitious dimensional space to understand and implement the conformal symmetry on the physical d-dimensional space. Okay? Why? Again, because in this d plus 2 fictional dimensional space, we know that these conformal transformations just act like rotations. Okay? Or Lorentz transformations, at least, because we have at least one more time dimension. And is the idea clear? So, how do we actually do this? If we can move to d plus 2 dimensional space, we introduce more degrees of freedom on our fields and so on. Okay, so we must eliminate these 2 additional degrees of freedom. Okay, and the question is, how do we do this? Okay, the idea would be to implement this conformal symmetry as rotations in this d plus 2 dimensional space, and then go back to the physical d-dimensional space. Okay, by imposing 2 constraints. And the question is, what are these constraints? Okay.
Isn't the conformal group 2 dimensions higher than the space-time?
What?
I mean, you have a d-dimensional space-time,
Yeah.
and the conformal group related to this space-time has d plus 2 dimensions, right?
No, it's just that you have a. If you want to, we can never talk about this. Okay? If you want. And then you have the d-dimensional spacetime, and the group is that. Say you have d-dimensional Minkowski spacetime, so the group is SOD2. But you know it acts non-linear. Okay? So that can be cumbersome to. This non-linearity can be cumbersome to actually prove, say, the quadratic part is related to yes CT, okay? The scaling part's linear, okay? It's containing the linear there. So it can be cumbersome to check if your theory is conformal invariant, meaning invariant on the SCT, because it acts non-linearly, okay? The scaling invariance is usually easy to check if your theory is scaling invariant or not. And what this method does is, if you look in this d plus 2 dimensional space, we know that in this space, the conformal transformations would just be like rotations. Conformal transformations are just rotations in this d plus 2 dimensional space. Okay, conformal transformations in d dimensional space is just other rotations in d plus 2 dimensional space. Okay? And we can guarantee that we have something that is invariant under rotations in this d plus 2 dimensional space, and we have say a receipt to just project back to this d dimensional space such that the conformal invariance is preserved, then we will guarantee conformal invariance in the physical d dimensional space without having to go through this non-linearity. Okay, that is the whole idea. That is why this is useful. And this will be the quickest way to get the correlation functions in a set in d-dimension, okay? In d-dimensional, so I already gave you our hint. Okay, we must put 2 constraints to project back. And okay, this is another name for this formalism. Some people call it projective conformalism, projective formalism, or projective method. Okay, because you do everything in this d plus 2 dimensional space, and then you just project back to the dimensional space. Okay, some people call it projective con. And these constraints must preserve conformal invariance. Okay, you must preserve this conformal invariance in d plus 2 dimensions. So, what are these 2 constraints? Anyone wants to take a guess? The hint is already written on the blackboard, in this blackboard.
It's not important, but I think the knee should be upper. The 2 last, the knee should be upper, right?
I probably just committed this
It's
mistake in
not
everything that I wrote, just correct it.
Yeah.
Also in the second.
Yeah, it doesn't. Yeah, that's it. I guess I committed this mistake in my notes. I always write it, I wrote like that. But okay, if it's so clear, it doesn't matter. Anyone wants to take a guess? The first constraint, the answer is already written on this very same blackboard. No? You must. We're sitting d plus 2 dimensional space. What is the only d plus 1 dimensional surface that is preserved? Remember, we're in say we start from Euclidean space. We have Euclidean space, physical space, in d dimensions. Then we add 1 more space dimension and 1 time dimension. So we have a Minkowski space, we have a d plus 2 dimensional Minkowski space. What is the only d plus 1 dimension?
Oh, the cone.
The cone, the light cone,
Yeah,
yeah.
the light
So,
cone.
okay, I'll write the condition, then from the condition I'll introduce the new notation. We must impose that, we must restrict to the light cone. Okay, so I'll just introduce the notation in this D plus 2-dimensional space. I'll call the coordinates big X, okay? And the indices will be capital M or capital N, just like I did for the construction of that matrix, okay? Again, these capital indices M or N will run over mu, okay? Meaning D, there are D indices here, and D plus 1, and D plus 2, okay? So, this first constraint in this notation translates to, okay, I'll just erase this. Translates to x squared equals 0. Okay? That is the light one. This is the first constraint. And say we'll just take this and solve. Okay, before that. Since we'll be on the light cone, we'll make a coordinate change that is convenient when we lie on the light cone only. We'll introduce the light cone coordinates. Usually, if we just had the, say, Cartesian coordinates, this x mu would be big X mu, which is just, if you want the lowercase x from the d-dimensional space, be it Euclidean or Gaussian. Then we will have a x d plus 1 here and an x d plus 2 here. Oh, sorry, big X. Alright? Since we're relying on the light cone, and we're relying on a light cone relative to this new time direction, okay, this would be the time arc. Okay? If you read stuff from Minkowski, we also have a time arc direction here, but we just forget about it. Okay? We construct the light cone based on these two coordinates. The transformation, the change of base is given by here. We produce x plus, so just call x d plus 2 minus x plus 2 d plus. Right? Okay. And this, okay, or we already guessed it, minus x equals 1. Okay. I just construct these two new coordinates with the two directs I introduced on physical space. Okay. And with these guys, okay, so before the d plus 2-dimensional line element will just be this. Okay, we would read if you split this. Minus, because this one is the time direction. Okay. This is in Cartesian coordinates, so in light cone coordinates, this becomes a bit simpler. It becomes, I'm writing this d plus 2 just reminds us the line element on the d plus 2 dimensional space, because later on, of course, we project back to the d dimensional physical space and we have a ds squared d. Okay? But it's not important right now. This will be just what we had before here, dx mu minus this cross term. Okay? Okay, that's how the line element changes. Some people may put 1/2 factors here and so on, or stick to these conventions. And so the first constraint in these coordinates reads x mu minus x plus x minus equals 0. Okay? On the right column coordinates. So we want to eliminate, of course, these two new coordinates. Okay? So we can solve this one. I guess we solve it for x minus. So this becomes x minus will just be x mu. Okay, let me just write one. To copy it. So x minus will just be under x plus. Okay? This is a formal solution, okay? For now. Any questions? This is the first constraint. Okay? We now officially sit at a d plus 1 dimensional space, that is the line column. Okay? Any questions? No? So conformal transformations, let me just try and draw a picture here. What we're doing is and say I'll just here just put this will be I'll order the physical space coordinates here. And here like on this direction is x plus, and this direction is x minus. So you see the white areas. So the conformal group on this d plus 3 dimensional space should just act as rotations again. So meaning that x prime m is just Lorentz matrix. For example, if we start with the Euclidean space. This is just the action. Measures in the d plus 2 space. Okay, linear action on the d plus 2 dimensional space. And again, since we're lying on the light cone, this will be preserved, okay? So this means this will be a map between points on the light cone. Or if you prefer, it would be a map between light rays, okay? Since okay, this is a point, so any other point here will define a light ray, okay? So what this transformation is doing is just mapping different light rays. Any questions?
But since the space is D2, there has two light cones.
If you start from with a Minkowski,
it's D plus 2. So it has
if we started with d-dimensional Minkowski space, then we will have a second light cone on the. We could construct another light cone here in these coordinates here. Okay, I'm just ignoring it. Okay, I'm just focusing on the light cone we actually introduced.
But
because
the
we must
time
introduce.
lights are d plus 1 and d plus 2. They're both time lights.
No. Remember, we introduced one space dimension and one time dimension when we were discussing this. Okay. Okay, so the d plus 2 I'm taking as the time like, and the d plus 1 I'm taking as the space like direction.
Yeah, because SOD, 2, they have two.
If we start with the d-dimensional Minkowski space, physical Minkowski space, yes, we would have two light cones. We have this light cone that is built from the two extra coordinates, and we will also have another light cone here. What I'm doing is just ignoring this light cone. Okay? I mean, I just cannot draw this. I mean, it's d-dimensional.
No, so this space, this d plus 2 dimensional space, it is actually d plus 2 space and one time coordinate.
No, it's d. It's okay. First, you're starting with the physical Euclidean space or physical Minkowski space?
No, Minkowski space.
Minkowski space. So we have physically we're starting from d minus 1 space dimensions and 1 time dimension. Okay. This is our physical space.
And in that space you have the conformal group, which is isomorphic to SD2.
Which acts non-linear. So we will like to get a linear action by going to a d plus 2. When I say d plus 2, I'm just telling the total number dimension. I'm not caring about which are how many or which
But now my question, you said these large x coordinates, they are coordinates in this d plus 2 dimension space.
Yeah, which is, if we start with the physical Minkowski space, we would then have a d
Space
dimensional, d space dimensions, and we have 2 time dimensions. And
And
then we would have a 2 light. We could think about 2 light cones here because we have 2 time-like coordinates. And I'm just focusing on the light cone built from the 2 extra dimensions that I introduced. Okay? I'm ignoring the other light cone that would be here. It won't matter for us. Okay?
But large x d plus 1 and large x d plus 2, they're both time-like. That's my doubt.
No, the other thing.
Since they are coordinates in the d plus 2, these large x are coordinates in the space.
Okay, I guess. Okay, let me try this. I guess you're getting confused with all these light names on the blackboard. These first mu coordinates
D-dimensional
are like in Minkowski space. If you take Minkowski space for starters, we have time and space. Okay, physical. Okay. So we have one time here and one time here. We have one time at the start and one time at the end. Just how I chose to organize this. There's some people that put this here in the front, but it doesn't matter. Okay. And then we introduce these light cone coordinates. Okay. I could introduce light cone coordinates for say this time dimension and one other spatial dimension on here.
No,
Okay, I could, but I'm just not doing it. I'm just focusing on the light cone built from the 2 extra dimensions that I introduced, because in the end, that is precisely the 2 dimensions I want to get rid of. Okay. So, is it clear?
No, it's clear.
Any other questions?
I still don't know where this restriction comes from. Like, can you give an argument
Where it comes?
where it comes from? Like, how can I see that this is a restriction? I mean, you just
This?
that
What,
you have
this constraint?
Yeah, this constraint. Yeah.
Because I can just solve. It gives me
No,
an
this I
equation.
understand, but I still don't know why I should restrict to the light cone.
Because, okay, I spoke but I did not write. Okay. Because is where it.
Because it is invariant.
The the light cone is invariant. Okay, these transformations here are just Lorentz transformations. Lorentz transformations.
Yes.
Okay, Lorentz transformations leave the light cone, preserve the light cone.
Okay.
Okay, so if you chose any other d plus 1 dimensional surface that is not the light cone,
Yeah.
then this surface is not preserved on the transformation. So if I choose a d plus 1 dimensional surface that is not the light cone, and then I make a conformal transformation, a Lorentz transformation that I need in this space, then I'll end up with another surface that is not invariant.
Yeah.
And then this will spoil the conformal symmetry on the dimensional space. Okay?
Yeah.
So that there's
You only
this
said it like
is the only preserved surface.
Yeah.
D plus 1 preserved surface. Any more questions? Okay. So we're running out of time, so I'll just here's what I'm gonna do. I'll write the second constraint. I'll briefly talk what it means, but I suspect that this will trigger a big discussion. Maybe so. I'll just write it, say maybe a few words about it, but we'll continue from this in the next section, just so you can take a 1 week thinking about this constraint, because this is the harder constraint to understand. The second constraint is okay, first of all, relying on the light cone, okay? This light cone, d plus 1 dimensions. So we must get rid of another dimension, okay? So we would inevitably end up with, say, some section here, like let me just, for clarity, I can use colors here. We end up with, say, some cut here in the light cone, okay? Some closed curve here, it could be this way, could be here, yeah, this way, okay? Whatever it is will be a section of the light cone, okay? So we get rid of normal coordinate. And this will be a condition. So here we got rid of the x minus coordinate. So we need to get rid now of the x plus coordinate. To get rid of the x plus coordinate, we just impose that this is any function of the other coordinates, okay? This will be a section of the light cone. In principle, we have x minus here, sorry, but I'm already supposing that I got rid of the x minus here, I already solved here, okay? So this is what it, this is what it's going to be. The actual constraint is how do we choose this guy, this function, okay? So far this is a general function, and this is the maybe what might take some thinking about, but the answer is take a projective constraint. Meaning, if I have a point xm on the light cone, okay, this xm belongs to the light cone. Okay. I'll take any point on the light cone and I'll identify it. It's like an equivalence relation with another point that is proportional to it. Okay? I introduce this equivalence relation. So if I in pictures, okay, I can erase this. In pictures, so if you have a here's the icon, and we have a particular light ray here, okay? And then I can just say that this point is equivalent to this point here, on the same light ray, but later on or sooner, okay? And I do this for every light ray, okay? I have this point is equivalent. So what I'm effectively doing be a map, since we're in the light cone, this will be a map between light rays. So what this equivalence relation is doing is that it's actually a map between points of different light rays. Okay? If I start from a point here in this ray, and then do a conformal Lorentz transformation in this space, I will keep sitting on the light cone because it's preserved, but I might say end up here at this point. And another light ray, say up here could be down, and it doesn't make any difference. And then what I'm saying is, okay, I will say that this point is equivalent to this one. So I'll just kind of scale back. Okay?
Basically, you're restricting the norm to unit.
Sorry?
Basically, you're restricting the norm to unit.
Yeah, almost. I could restrict. That is actually the constraint I'll take. So it could be any section, right?
Yeah, rotations to move like this, you need rotations. The boosts,
Yeah.
they only
Yeah.
take you
If
farther.
I go from light ray to light ray prime, say,
Okay.
this is a Lorentz transformation, okay? What is not a Lorentz transformation is this is the first step, if you want. The second constraint comes here. I just say that I'll choose a section, and this statement is the section, whatever it is, the section x plus f of x mu is not preserved. Right? What is preserved is the light cone. Okay. It's not the section. Any section of the light cone is preserved by the Lorentz transformations. Okay. So if I choose, I ran out of corners here, but say if I chose this section here, like on the horizontal. Okay. If I do a conformal Lorentz transformation, I get out of the section. Well, what do I do then? I introduce this projective constraint and say, okay, like this point is equivalent to this point. So I go back to the section.
Perfect.
Okay. So. And then okay, I could just take any constant here, and for simplicity, I'll take what you said. I'll take f as say 1, just 1. So this means that this will amount to x plus equals. Let me just see if I'm not missing. Okay, it might not be able to write this one. I don't write it. I could do something here, and then we'll continue this on the next lecture. What might?
Just one question. What you call the section that is not preserved is the two circles or the
Any section.
Huh?
Any section.
I mean, when you do a Lorentz transformation, you just go from one point in any of the circles to another point in any.
I go from one point of the light cone to another point
Okay.
of the light cone.
You can go you can make a Lorentz transformation, go from this point to this point here, for
Yeah,
example.
and I could define a section, from this point and going around. But then I could start from the same point I started and do another Lorentz transformation and end up at another arbitrary point that does not lie in this section. You just define.
What
So
you
that's
call-
why we need this projective
What
constraint.
you call lattice transformation is both rotation and boost.
Both rotation induces, yeah.
Okay.
But just like rotation. Like those are just rotations in the
I'm just
axis.
trying to figure out what's the motivation for the.
Yeah, that's why I told that the constraint takes a bit of thinking.
Yeah.
But I guess I don't know if this helps, but you might think that as motivation for this, for identifying points on the light cone, you might remember that a light cone specifies this. Say take two new vectors. Take a vector. Okay. Just an example. Okay. This is a new vector, right? This is a time direction. If I can put a norm, it will be 0. Okay. And then if I define any other new vector that is just proportional with a constant here, then this implies that they are orthogonal. Okay. That's why you don't mix anything special happen. Okay. I don't know. I'm not sure. I just say this. I don't know. This maybe might help as to why we choose to identify points on the same light ray. If I take another light ray, say another new vector, say V. Just putting the if I take another new vector, but that is not proportional to this, for example, -1, 1, 0, 0. Okay? This vector is not proportional to this one. Okay? Go with this. And then if you compute this, then it will just be 1. Okay. 1 vanish. Okay, so maybe you can start from there and say, okay, maybe this is the statement that these guys lie on the same light ray, okay? And this is showing you, since this is different from 0, this shows that these guys are different light rays. They're both light rays, but different light rays.
Yeah, the only light vector that is orthogonal is parallel.
This is a basic fact about Minkowski space. Okay, no vector is orthogonal to say vectors proportional to itself. Okay, for a constant here. Okay, any constant number. So maybe you can start from this and think about the project constraint and start from this. Maybe this might help.
It's interesting. I mean, basically, you map the d dimensions into 2 hypercircles. In fact,
My imagination is not that great, but
it's,
if you want to write this,
it's 2 hypercircles, and you have to do exactly that. You map the.
Yeah. The section will be a circle, but the point is that just as we talked about on the first constraint, the only surface that is preserved by the Lorentz transformation is the light cone. So that's the first constraint, obviously.
Yes.
And then, but we must get rid of one more coordinate. And the thing is, if I get rid of any other coordinate, I'll end up inevitably with a section here, whatever it is. And the point is, this section is not preserved by the Lorentz transformations. But this fact about Minkowski space comes back to rescue us, okay? Because it allows us to introduce this projective constraint. If I lie on another section at a different point on the same light ray, then I can just say that they're equivalent. It doesn't matter. It's as if I'm lying in the same section. Okay? I hope this explains why to take a projective constraint. Is this clear? Okay. This fact that I take this guy constant is less obvious. And this one was last lecture. I'll just review this, the first constraint, the second constraint, and then we'll do some actual computations and see that f equals a constant. F equals a constant is the solution. It's the solution we want. Okay, we will see this in actual computations. And then for simple instances, any constant, we just take it to be 1 for simplicity. But this, I hope at least next week you get comfortable with this fact and understand it. And this one we will understand next lecture, next week. Okay? This one we might you can just relegate to next lecture. But I hope you can understand the why the projective constraint. Everyone understand why the projective constraint? It's kind of the only option. Almost. Any questions?